Did you know the Egyptians were the first to use a chemical water treatment? Thanks to alum, potassium aluminum sulfate, the Egyptians found how to coagulate particles out of cloudy water, speeding suspended particle settlement and facilitating filtration. The discovery of this purification technique, also known as coagulation, was reported in several pictures found on the wall of the tomb of Amenhotep II and Ramses II. In the coming years, there were several breakthroughs in improving water treatment. Hello and welcome to another episode of Crosstalks. My name is Adriana Costa and I will be your host. This podcast series by the UT Austin Portugal Program will walk you through the wonders of science-business collaboration. We will be exploring emerging topics in advanced computing, medical physics, nanotechnologies, space-Earth interactions, and technology innovation and entrepreneurship, as we delve into the program's industry-driven research projects. From the first Roman aqueducts for carrying water from one place to another to the invents of James Simpson, an English engineer who built a sand filter for drinking water purification, centuries of evolution allowed us to, nowadays, just open our faucets in our places and drink potable water in less than 2 seconds. Despite all the technological advances, some inorganic contaminants remain in the water even after treatments and purification methods, posing several risks to human health and the environment. The United Nations, through its Sustainable Development Goals, calls for all countries to act in promoting clean water and sanitation, aiming at improving water quality by 2030. However, neither conventional nor advanced water treatment technologies have ticked in efficiency and environmental criteria to tackle this problem. In this context, the NanoCatRed project's team is developing nanostructured catalysts that can achieve a step change in the performance of catalysts for hydrogenating inorganic contaminants in water. In short, the team is testing how nanostructured catalysts can turn contaminants such as bromate, nitrate, or perchlorate into non-harmful products through a chemical reaction. To find out more about this ongoing research, we invited the coordinators of NanoCatRed to make it water clear. Salomé Soares, assistant researcher at the Faculty of Engineering of the University of Porto, Sérgio Silva, founder and CEO of ADVENTECH, and Simon Humphrey, professor at UT Austin's College of Natural Sciences. So, hello, Salomé, Sérgio, and Simon. Welcome to Crosstalks, and thank you for accepting to join me today.
Hello.
Hello. It is a pleasure to be here. Thank you.
Hi, good morning from Austin.
Good morning from ADVENTECH.
Good morning. Okay, so first of all, I would like to ask you about the idea behind the project, NanoCatRed. Why did you decide to study this solution to remove inorganic contaminants from water? Can you start, Salomé?
Yes, for sure. Actually, the idea for the NanoCatRed starts at FEOP. We have been working on nitrate, bromate, and also perchlorate hydrogenation for the last few years using nanostructured catalysts at a lab scale. When you know about this call, we are sure that it will be an excellent opportunity to join a consortium with knowledge on this topic to work together and implement this technology at large scale, like a pilot plant, and also to overcome some of the disadvantage of this technology by combining new methodologies for the fabrication of improved nanoparticles and or supports that can improve the activity, selectivity, and stability of the active metal phase during the hydrogenation reactions. So we contacted the group from UTA, which we already knew that they have a large experience in hydrogenation reactions to remove these ions, and also in developing nanoparticles with enhanced properties. And also we have contacted INL, which is one of the other partners of this project, which is already have experience in developing and characterization of nanomaterials and nanoparticles. And then once this call for this specific project must be led for a company, ADVENTECH came as a leader of this project since they have a large know-how in the development of advanced environmental technologies for water treatment, and they were the right partner to develop the pilot plant. So we construct this NanoCatRed project to bring together a group with large experience in the areas of nanomaterials and water treatment technologies to remove these inorganic contaminants from water. And in fact, it has been an extraordinary experience for all because we are sharing all our knowledge to improve this topic.
Thank you, Salomé, for giving me the overview of how everything started. Your project is developing this solution to remove inorganic contaminants from water, as we have said before. Simon, what exactly are inorganic contaminants? And if you can explain why their presence in water entails risks for human beings and the environment.
Okay, so I think inorganic contaminants in general is a very broad term, but in this case, we're talking about contaminants that are water soluble, of course, and that contain oxygen atoms. So we're talking about highly oxidized species, perchlorate being a form of the chloride ion that also carries oxygen. And there are several biologically understood pathways by which those kind of species in the body at the cellular level can lead to release of oxygen species that can in turn cause cancers and so on, that are really not fundamentally well understood in terms of how much of a contamination, how long an exposure one needs for cancer to be prevalent. But there are enough links to show that these kind of species in water at least are detrimental to health. And so obviously their removal is important. And they're the kind of species that vary in concentration between water samples from one place to another, depending on where the water is sourced from, the rock formations, several other factors that can change whether these species are present in higher or lower amounts in different regions.
Thank you for this very simple explanation. I'd like to ask if Salomé or Sérgio want to add anything.
I can add something in point of view at ADVENTECH, the company. The nitrates, bromates, and perchlorates have impact in some of our clients, and particularly in the south of Portugal, where we have large crops and the agriculture is very intensive. There are many nitrates, and in the water treatment where we use ozone or UV radiations. In some of our clients, we have productions of bromides, since the raw water is have bromides. So it is a problem in some of our clients, and our concern is to have a technology that we able to treat and solve this kind of problems.
Thank you for adding your input regarding your perspective as the CEO of your company, ADVENTECH. Back at Salomé, can you tell us how and where this contamination can occur? And are there any contamination sources that we should be concerned about?
Actually, some of these contaminations can occur naturally, but most of them are related to human activities. And depending on the compound that we are studying, their presence can be do different things. For instance, in the case of bromate, they can be formed naturally in surface waters, but it also can be related with seawater intrusion or discharge of effluents. But the most common one is related with water treatment plants as a result of the ozonation of bromide-containing waters, which can limit the use of ozone in treating of organic pollutants, because this inorganic pollutant can be formed. When what concerns to nitrate concentration, it can be found more constantly in the last years, and it is mainly related with the human activity, like the use of fertilizers in agriculture. In what concerns to perchlorate, they are more related with the manufacturing of explosives or rockets. So these are the main contaminations that can occur by these pollutants, and it is the reason we need to consume all these waters, and since they can cause several damage to human health, they need to be removed by different technologies.
It's very interesting to know how different chemicals have different sources. And just out of curiosity, is there any data that can link us, for example, if this contamination is increasing in time due to human activity?
Yes, there are several evidence of their presence in water and of their increase in the last years. This evidence can be found in information collected by several relevant authorities in the world, like the United States Environmental Protection Agency, EPA, the World Health Organization, but also by the European Commission. The presence of these anions in water in concentrations higher than the desirable are demarcated as a problem to approach in a near future, and it is foreseen to be included in the legislation of several countries. This is the case of perchlorate, for which in the last years exists only an official recommendation since 2015 regarding to improve the monitorization of this contaminant in water and also in food. So it is expected that in the coming years, with the information collected from this data, that it will be included in the regulation of water. In the case of bromate, it is also have already a guideline provided by the World Health Organization of 10 ppbs, but their presence is already regulated by the Drinking Water Directive in the case of the European Union, but also by the EPA. Just an example, here in Portugal, it can be found information about the water collected quality measured by accredited laboratories, and this information is published by ERSAR, and it can be found there that the concentration of bromate is accomplished in most of the waters analyzed, but in some cases can be found higher values than the legislated. And this is mainly detected in industrial wastewater treatment plants in which bromate is formed during the ozonation of bromide-containing waters. In the case of nitrate, this pollutant is already being followed since the beginning of 1991, where it was published the first nitrate directive, and consulting this directive, we can find several informations concerning the legislation and zones where it can be found more nitrate, and the last reports reveal that here in Portugal we have 11 nitrate vulnerable zones where the nitrate concentrations surpass the 50 milligrams, which is the legal limit imposed for nitrate.
Now, let's dive deep into your project, which proposes a solution to this environmental problem. The project's goal is to develop a technology which is capable of removing oxygen-containing anionic contaminants, also called oxanions, from water. Simon, can you give us an overview of what you are developing?
Yes, certainly. So oxyanions in general are what we were talking about a short while ago. So for those who are not aware, any anion is something that's negatively charged, and an oxyanion in this case carries oxygen. So chloride Cl minus is a common anion, but it can also be ClO minus, ClO2 minus, ClO3 minus, or ClO4 minus. So it can carry different amounts of oxygen with it. And those are the oxygen species that are more likely in degradations to form radicals and other species that we don't want to take into our bodies. So the challenge here is to find alternative ways, at least to legacy technologies in the potable water space, to selectively remove these oxyanions. And what we're trying to do is an approach that would degrade those anions in situ and produce only more benign materials, which could be still in solution or could be gases, for example, that are released. Current ways of doing this, and you can imagine that obviously drinking water is a large volume thing. So you've got a huge amount of volume of your produce, as it were, that you have to process. And these anions are on a very low concentration. So you're talking about maybe parts per million, which can still be problematic for intake. So you obviously need something which is selective and something which can target these species. Traditionally, they can be captured from water with materials that effectively absorb these types of anions, but then those materials themselves have to be regenerated, and something has to be done with the anions that have been captured. What we're trying to develop is a catalytic approach, by which we mean using a catalyst that's in contact with the water itself and would selectively bind to these oxyanions, then react with them in the presence of hydrogen gas in this case, to effectively reduce the oxygens back to ultimately water, and then produce the naked anions, chloride, bromide, or in the case of nitrate reduction, we mentioned nitrate, which is NO3 minus, and also nitrite, NO2 minus. Those can actually be reduced to give water and also nitrogen gas. So obviously very benign products there. The obvious challenges, there's one challenge that we don't talk about in our group because we're not specialized in this. And obviously a project like this has many facets. One of the problems is where you source the hydrogen from. How could you get enough hydrogen? We're not really focused on that. We're assuming that there would be a plentiful supply of hydrogen, at least for this process to work. But then in our case, we are adding hydrogen gas into the aqueous phase. The hydrogen finds the catalyst species and is activated itself to give hydrogen atoms from H2 molecules. And on the same catalyst surface, the oxyanions are bound. They react with the hydrogen to give water by stripping the oxygens from the anion, and then the anion is released back into solution. So that's the overall plan. And that's what we're investigating with model catalysts that can then be scaled up to the pilot plant scale with ADVENTECH.
So basically, let me see if I get this right. So you're basically using other chemicals that can connect with those bad chemicals and then release water and a more benign solution, or a more benign chemical. Is that right?
That's right. And because this is truly catalytic, the catalyst, which we'll talk about, I think, in more detail, which is what we're kind of designing and trying to refine, those catalysts are never obviously consumed because they're truly catalysts. They may become poisoned over time and need replenishment or replacement, which is what is important to us in our studies. But yeah, they are effectively able to perform this chemical reaction in situ in the water phase, a little bit like the gas phase reaction that happens in a car catalytic converter, by which nitrogen oxide containing species that are generated in the engine, NOx type gases, which we don't want because of acid rain and human health, are therefore converted back to benign products like water, oxygen, and nitrogen. We're doing the same thing in the aqueous phase with water.
Oh, interesting to see the parallel with that. I don't know if Salomé wants to add anything, since this is a collaborative project which has a lot of other partners and other perspectives. So if you want to give your perspective, go ahead.
Just to add a little bit more information what Simon already said. more specifically, what we are working on are we are trying to design these nanocatalysts to apply on these reactions, and we are trying to using two different methodologies. One of them is we are trying to tailor the support that we are using for these catalysts. And another approach is related with the production of the nanoparticles. So we are trying to combine the tuning of these two materials to support and also the metallic parts in order to improve this catalytic process. We want to tune these catalysts to be also applied at a large scale more at the end of the project in the pilot plant that ADVENTECH is developing.
Okay, thank you for bringing your perspective. Sérgio, do you want to add anything?
Yeah. So ADVENTECH take the results obtained in the tests of Austin and Porto, and we'll design a pilot reactor. We do the scale up of the reactor, of lab reactor, into a semi-industrial pilot unit. And we will test the best nanocatalysts developed, and we tested in the medium long-term tests in real conditions. So we evaluate the results under real conditions of this new nanocatalysts and this new technology.
So back at Simon. So one of the things that I saw while researching your projects and getting more information about it is that you're trying to overcome the main problems with conventional water treatments with what is called catalytic hydrogenation. I can see that you have probably already mentioned some of it, right? But I would like to know, what are the problems with conventional water treatments, and how is NanoCatRed technology helping tackle them?
Yeah, so to take a slightly deeper dive into this, as we discussed earlier, catalytic processes to treat water are not necessarily the dominant technology yet, and there's some reasons for that because of cost and the application. And a lot of these processes that are used for potable water treatment are plants that are built out already, and to find a drop-in technology that can be a useful replacement is often a challenge. And I'm sure Sergio would know much more about that than I do. But the primary issues that we think about when we're designing catalysts for this purpose is, to start with, the cost of the catalyst itself. A major issue is that one or two of the metals from the periodic table that are known to be the most effective at activating hydrogen gas under these types of conditions to convert hydrogen into a reactive form that can be used for these purposes requires metals that are scarce and expensive, platinum, palladium, and in some cases, rhodium, iridium, metals that are not easy to come by. And so what we'd like to do is be able to make those kind of catalysts more economically viable by dilution, effectively, of those expensive, scarce metals using secondary metals that are much more earth abundant. So we're talking about metals that you could find in your house and we don't really think of as being expensive, like copper that's used to make plumbing pipes, or even silver, which people think of as being a semi-precious metal but doesn't have that much value in industry. So we combine those ideas and take into account what Salomé had mentioned, which is also that these catalysts, which are nanoparticles, meaning they're clusters between, say, 2 and 10 nanometers in diameter. To put that in perspective, you're talking about hundreds of thousands of atoms per cluster, given that a 2 nanometer particle, for example, would contain a few hundred atoms. So a 10 nanometer particle contains a few 100,000, but they have very small volumes, very large surfaces, which is important so that we're exposing the metal to the solution so that the reaction can take place. That's the idea of using a nanoparticle rather than a block of metal. The second problem there is that you need to support the nanoparticles on a substrate so that they don't float off into solution and themselves degrade. And this is what we refer to as the chemical support. That support is a firm attachment for the nanoparticles. It also means that the overall material, the catalyst material itself, is insoluble, which makes it able to be extracted from the solution and so on. It can be pressed into pellets and shapes that are useful on the larger scale for water treatment. But those supports themselves also do important chemical things to the process. So the chemical properties of the support can beneficially add to the qualities of the nanoparticle on which it's supporting. So the whole thing can be a synergistic system. So we have a big playing field, you can imagine now, of variables, because we have what is the support, what is the chemical nature of the support, what is the nanoparticle construct. And so to wind this part up, I don't want to talk too long about this, but what we do in our lab and what we had been doing before for other applications in oil and gas actually, and then realized that this could be applicable to this water treatment application, is taking nanoparticles that are made of precious metals using a microwave-assisted synthesis technique. And importantly, that is scalable. So we're always thinking about how can we take what we learn in the lab and do something that could also be made on a kilogram-ton scale. So we use microwave-assisted heating to quickly, rapidly co-mix two or more metals. For example, we take some palladium, which we know does this important chemical reaction with the hydrogen. We mix it with copper or silver or a combination of metals to dilute so that the nanoparticle has a mixture of those atoms. It's an alloy. And therefore, we need less of the expensive metal to make the nanoparticles, therefore making the catalyst itself more economically viable, but also potentially the alloy itself can have beneficial effects which make it more tunable electronically to be good for this application. And then we pass these particles over to Salomé's group, who puts them on different supports, and then the iterative process of looking at the catalytic properties continues from there.
Very interesting to know that it's a lot of variables here. So it's a matter of costs. It's a matter of using things that are more abundant, right? And then using such small particles to increase the surface area and increase, I would say, efficiency of the process. You're close to completing the project. It's expected to end sometime this year, 2023. I want to ask Sérgio, how far have you come with accomplishing the goal set at the start of the project? And I would like also ask if you will have a market solution at the end of the project. If not, what does it take to get it to the market?
So at the end, we will not have a ready-to-market solution. So as I said previously, we have some challenge first. So we'll test in the pilot plant the technology. We will test the different nanocatalysts developed by Austin and Porto, and we have to test it under different real conditions with different waters and wastewaters during a long period of time. So we'll test the catalyst efficiency using water with different compounds that the ones we are testing now. So the materials will be contact with different matrices, and only after all the operational details are very well known, we will be capable of letting the unit operate in the automatic mode. And after that, we need to work on robustness and stability of the technology and solve all the problems and mechanical problems and problems with control problems that will appear later. And after that, we need to solve one important challenge, which is the commercial production of nanocatalysts. And yes, after this, all these steps, we'll be able to have a ready-to-market solution and be able to spread the technology in the market. So it's a long way until I have a ready-to-market solution. But at the end of this project, we have a technology that we will able or not to solve this problem of oxyanions in the water.
It is indeed a long journey ahead of you to get this to the market. Imagine this would eventually get to the market for sure, but how many years could that be possible?
So from our previous experience with other kind of technologies, usually never less than 5 years until I have a robust solution to the market. So at least in the better cases, 5 years is the time frame that we have to develop a commercial solution. But many times it takes longer than that. Because when we spread the technology in worldwide markets, we need to have a very robust and stable, and we need to solve all these problems I referred previously. So it takes a long time.
For sure, you need to be very persistent to make it all work, and I'm sure you are.
So the main problem is the time. So many times it's not the difficulty of the tests or experiments, but we need to do it for long-term tests, and only after the long-term tests we'll be able to have or not a stable technology. So time is the main problem, because we have tested through the long time.
Yeah, I would say it's a necessary evil, because if we didn't take that much time, probably the project wasn't as good as it could be, right?
Yeah.
So imagine that 5 years from now, you have a solution to the market and it's going to be in the market. Could you tell me who will benefit the most from this technology?
First, industry, and also the reuse of water. As Simon said previously, most of the nitrates, and mainly bromates and perchlorates, are originated by many cases oxidations. So it's like ozone in the water. If the source water have bromide, for example, and we disinfect it with ozone, we will produce bromides. So and in the same cases, if you make UV at the end of wastewater treatment plant, and this plant have bromides, same occurs. So the main clients for this kind of technology have the reuse of water and the treatment of water from sources that have this kind of problems. And the most important thing is that this kind of technology is not a separative technology like filtration, osmosis, so on, and the adsorption process. So we'll not concentrate this kind of oxyanions in another matrix.
Okay, thank you for your input. Now, I want to start to ask Salomé. So this is a collaborative project between institutions from Portugal and the University of Texas at Austin. And I'd like to ask Salomé, how important was the UT Austin Portugal Program to roll out this project?
In fact, all of us know that inter-Atlantic collaborations are not as easy to establish as national or European ones. And this opportunity proved to be very fruitful, resulting in outcomes that could not be achieved by the individual parts. So therefore, this UT Austin program had an important role in the construction of this consortium, giving us the opportunity to join all these teams and to work on the development of these technologies. Of course, without this program, we are not able to join all these people and work on this subject.
And if we do things alone, it's also no fun to do things. And any perspectives from the UT Austin side, Simon?
Yeah, to echo what Salomé has already said, it's actually, this problem we're tackling is obviously a global problem, and the problems are seen from different viewpoints in different regions, whether that's for political reasons or for health and safety reasons, whatever it might be. So collaborating multinationally is important so that everyone has a better understanding of these types of problems, as well as more fundamentally bringing together the skills and expertise that different groups in different regions have. So this is really unique that we have this University of Texas Austin Portugal program, because it shouldn't be understated that actually it can be difficult to get money to do fundamental research of importance between certain countries, because there just aren't often ways to do that. Science tends to be funded nationally by national foundations. So we have the National Science Foundation, Department of Energy, for example, here. European countries tend to have their own funding agencies, as well as the European research community and so on. But working together can sometimes be difficult. So this has been a great platform to do that. And certainly, you know, we hadn't been able to work together before, but now that we have, I know, and I'm certain in the case of our labs, other labs at UT that have been involved in the project, Professor Charlie Worth and his group, Graham Henkelman and his group will actually continue to work with Salomé and her co-workers, and hopefully Sergio and partners in the future, because once a collaboration is formed, that's the roots and foundations of better things to come.
That's nice to hear, and we will talk a little bit more about it later. But first, I'd like to have the input of Sérgio and to understand how this partnership has affected, or the side of the industry, at least.
The partnership between the scientific community and companies like ADVENTECH is very important, and in this case in particular, we have the opportunity to share important scientific knowledge between partners, namely between European and US universities, which have different scientific background first, but also different methods of working and different points of view. And for ADVENTECH, it's very important to have this kind of scientific knowledge and the background that can give us the possibility to develop state-of-the-art technologies and to have the opportunity to solve some actual problems in the water, in the wastewater field. It's very important to have this kind of collaboration.
Thank you. So now going to the future of the collaboration, Simon gave some hints about this. So I want to first ask Salomé the prospects of continuing with this collaboration. Are there any?
Yes, in fact, they are. Actually, in parallel with this project, we already have a student from Portugal that is making a stay at the laboratories of Simon and Charlie. And we hope that this collaboration continue in the future, because during this time we found that we have common research interests besides these water treatment technologies. And for sure, we want to continue working on that. Of course, concerning all the consortium, we believe that we can still work together, and we are looking for other possibilities of fundings. We are looking for future UT Austin Portugal goals, even for exploratory projects, or also to further develop this NanoCatRed project to a higher readiness levels, because we are working at lab scale, and we are mainly achieve all the objectives that we have proposed at that scale. But as we already talked, we have a large way to go to implement this technology, so we can apply for other goals that will allow us to make this way, but also other goals. So because it is being a very good joint venture with all these partners.
I'm glad that you were able to find other interests or research interests that you can further develop. So that's very good. And Sérgio, would you like to add anything?
Yes, regarding future collaboration, I think when a team works well and people works all in the same direction, and we have a team with different backgrounds, it of course the collaboration after NanoCatRed will continue. I don't know if it is in the continuous mode, but from our side. Even we have a problem and we know some person with a strong scientific background, of course we ask to them if what they think about a particular case, and many times this kind of approach leads to other kind of projects and other kind of developments. So of course it's from our side, we are interested to continue with collaboration with people like Simon and Salomé, of course.
Yeah, we used to say that teamwork makes the dream work. So yeah, it's always better to do things together. Back at you, Simon. I don't know if you want to add anything to this topic.
Well, I would say that it shouldn't be forgotten that we started our project also corresponding to worldwide lockdowns because of the COVID pandemic. So I think we've done extremely well under those conditions, because it's only been the last, year, 18 months that we've been able to physically connect. It's been great to have progress made on Zoom and so on, but it was better when our group from Austin, or a delegation of us, got to go to Portugal this last winter for an in-person visit, because obviously more gets understood directly and everything works better if you can sit in the same room together. And then we're glad to invite Salomé and Portuguese collaborators to Austin in May, and we'll have another get together. But as Salomé already said, we have exchanged students. We are currently exchanging students, and that's great. That's part of the program, which is super valuable, because whilst the targets of the project are intrinsically important, it is also important to remember that we've been educating students throughout this project, and they've got an experience that other students will not have had. So there's something to be said for that.
Yes, that's definitely something very good to have, or to give these opportunities to other students. It's something that, at least in the UT Austin Portugal program, we also highly value, and we have initiatives to do so. And I hope that you have enjoyed Portugal, by the way, when you came here, although it was winter. So I don't know if you could experience our sunny days.
No, it was extremely enjoyable. Having grown up in the UK, I had been to Portugal a couple of times before, but this was a much more memorable visit, because a beautiful country and great food and great people, but it was all combined with a really productive work visit. So that was great.
Glad to know. Okay, so that was all the questions I have for you today. So I pass the mic to you to know if you want to add anything to end this episode.
Well, I just to thank you to the opportunity to being here to talk about our project and the progress that we are achieving under this UTA program, and to let all people know that it has been amazing working on this project. It is very, very good, as Simon told, meet all these people. We most of the time we talk by Zoom, but when we met in person, it was really nice, and it gives us the opportunity to see that we have several research interests, and it was much better to improve our knowledge. So I hope that we could continue this collaboration in the future. Thank you.
So we want from ADVENTECH, we want to thank you for UT Austin Portugal for invitation. That will help to disseminate this NanoCatRed project. And thank you for this international partnership program that makes possible the collaboration with the University of Austin. So thank you all.
Thank you from everyone in Austin, and obviously thank you, Adriana, for arranging this podcast so we could have a chat with one another, which was also enjoyable.
So now to wrap things up, I thank you again for Salomé, Sérgio, and Simon for being here. Considering I'm not from this field at all, I now know a lot more about NanoCatRed and about water contamination and how you're making turn things around. I'm hoping that the future is bright for you guys and for your future collaborations.
Thank you.
Thank you.
Thank you all for listening to this episode of Crosstalks. If you have enjoyed it, and even if you did not, we would love to hear from you. So make sure to subscribe and leave a review. For additional content, follow us at UT Portugal on Twitter, UT_Austin_Portugal on Instagram, or visit utaustinportugal.org. The NanoCatRed Consortium brings together scientists and business people from 5 institutions: ADVENTECH, University of Porto, the International Iberian Nanotechnology Laboratory, and University of Texas at Austin's Cockrell School of Engineering and College of Natural Sciences. NanoCatRed is co-financed by the European Regional Development Fund through the Regional Operational Program Norte 2020 under Portugal 2020 and the Portuguese Foundation for Science and Technology, bearing the seal of UT Austin Portugal. The total eligible investment is around 1.4 million euros, with public funding amounting to 1.3 million euros. The UT Austin Portugal is a partnership program in science and technology between the Portuguese Foundation for Science and Technology and the University of Texas at Austin, supported by the Ministry of Science, Technology and Higher Education in close collaboration with the Council of Rectors of Portuguese Universities.